All right, so we'll get started. So just as a quick recap of what we did last time. So on Friday, we sort of finished our introductory slide deck for computer networks or the internet. So, on Friday, we were talking about the structure of the internet, and then we said that it's really a connection of smaller networks all coming together, a hierarchy of smaller networks connecting to bigger networks and bigger networks. And essentially, it's a network of networks, and that's how it is. And we took a look at how regional ISPs are the ones, or access networks are the ones that give access to individual customers like you and I. And in order to provide global connectivity, these local ISPs would connect to global ISPs. And global ISPs would in turn have to talk to each other, connect to each other, and that can be done through, for example, peering links or internet exchange points and so on. And the hierarchy may not be, just local ISPs and global ISPs. You may have regional ISPs in between, and then large content provider companies such as Google, they may come up and deploy their own network. Then we started looking at, if we were to compare performances of different networks, what would be appropriate metrics. And we looked at three things: the throughput, delay, and loss. And delays and losses primarily come across because, losses come across because of an inherent nature of how packet switching works, where different users can send their packets at the same time, and then the router will store them first and then forward them. If you send at a much higher rate or at a higher rate than what the router can handle, then at some point the buffers will overflow and you'll have packet loss. And the same process where you come to where a packet comes to a router and it sees that other routers are waiting other packets are waiting in front, so you have to wait your turn, that contributes to the delay. And for the delay, that's not the only factor. There are three other factors. One was the processing time at the routers, just to process your packet, check for errors, see where you need to go, run the routing algorithm. And also the time to transmit the data packets on every link, and the propagation time, the time for the bits to cross the link from one end to the other. That's the propagation time. And so these are all factors that would contribute to the delays experienced by packets. And then we also looked at throughput. So throughput is basically the number of bits per second that you transfer from one end to the other, from the source to the destination. And you may look at it over a long period of time and take the average, or you want to look at the instantaneous value of the throughput. And the main discussion we had last week was that, if you are traversing a sequence of links in order to get to your destination, the effective throughput you will see would be determined by the link with the least amount of bandwidth that you're crossing. And that link has a special name. That's the bottleneck link. Right? So then that's what we saw. And finally, we talked about how we handle this whole complex problem of developing or designing computer networks. We made the case that when you want to have such a large-scale distributed system that spans the whole world, it's a very complex problem. And one way of handling such complex problems is to try and break it down into smaller individual pieces, which are much more easier to address. And it also helps you because you can change one particular piece of that whole puzzle and it doesn't affect the others, right? So that's the concept of layering. And last time we saw the 5 layers in the Internet Protocol stack: the application, transport, network, link layer, and the physical layer. We also saw that for each layer to do its job, it takes whatever the upper layer gives and adds some headers. And from the sending side, you start at the application gives to transport gives to link, and so on. And at the receiver, at the very destination, it's the other way. We go from the physical layer all the way up to the application. And at each layer, we strip off the headers that were added. So the application, at the end of the day, just gets the original message. And so this is sort of where we ended last time. And what we will do today is we will start on one of these layers. We'll start off at the transport layer. So the way we are going is we'll talk about transport layer, then the network, and then the link, and then we'll talk about application, and then other things, security, and so on. All right. I don't know, it's my machine's problem or the projector's problem or... Okay, fine. All right, so we will talk about the transport layer protocol for today, and I think definitely Friday. Hopefully we'll try to finish up Friday, but most likely it will go on to some part of next week's Wednesday. All right, so this is sort of what we want to do in this part of the module. We want to learn about transport layers. So basically, we want to see what are the functions that a transport layer protocol provides. And these functions, things like multiplexing, demultiplexing, reliable transfer, and so on. So we'll talk about all these functions that are provided, the goal, what a transport layer tries to achieve. And once we know about these functions and so on, then we will see how they're implemented in real life. So we will take a look at two real-life protocols, TCP and UDP, and we will see how things such as these are implemented in those real-life protocols. All right, so let's start off with the transport layer services and protocol. So what is the main job of a transport layer protocol? So last Friday we were talking about the protocol stack. And we saw that the end host, the sender and the receiver, my laptop, Google's web server, my phone, your phone, whatever, they all implement all the 5 layers, right? And the application layer, let's say at my laptop, maybe it's a web browser, wants to talk to the protocol, to the application. In this case, it's a web server, which is running at Google's machine. Okay? So my computer has a program, which is the application, which is the web browser. I'm running, let's say, Internet Explorer. That's the application I'm running. And this application, which is running here, wants to talk to the application on Google server, which is a web server application. Right? What the transport layer's job is, it gives the illusion to my web browser that it is directly connected to the web server. So it thinks that there is an end-to-end logical connection. My laptop doesn't know that from here I have to go through Wi-Fi access point, then to computer center, then to Singtel. My web browser doesn't care. When it talks to the transport layer, it says, can you please connect me to Google web server? And the transport layer says, yeah, sure, I will connect it to you. What happens below? Don't worry, I will take care of it. Right? Same thing with the postal service. You put your things in an envelope and you drop it in the mailbox, and you think that the mail will be delivered to your friend wherever it is. You don't care whether the letter will go on a truck or an airplane or how many post offices it will visit on the way. You don't care. You think that your mail is directly going to be sent to your friend. Same thing here. The transport layer provides a logical service. So any application layer protocol which says, can you do a transport layer job for me? Your transport layer says, sure, I will connect you to the application running on the destination side. That's the logical. So it's not a physical, there's no wire connecting me from my laptop to Google, right? So there's no physical connection, direct physical connection as such. But logically, my browser thinks that it's connected to Google. So that's really what it tries to do. And my application can give any size file that it wants to transfer. It may give a movie, it may give an image, may give only a credit card number. But the transport layer, what it does is it does the packetization that we talked about earlier. It will take the entire message and break it up into smaller pieces or packets. Now in the slide here, it says segment, right? Now, Historically, the way the internet was developed, it's not one engineer or one person who designs the whole thing. There are hundreds or thousands of people who work on it. And like we said, layers, there are different layers. So you work on a specific, it's not humanly possible for you to develop all the layers at the same time. So you work on a specific layer. Even if, let's say, some of you go on to graduate school, maybe, let's say you do your master's thesis or PhD thesis, and let's say you're interested in networking, you would pick one small problem in one particular layer. Right? So when I was doing my PhD many years ago, I was doing something related to TCP. One specific problem within one particular layer. So, I have a group of friends who are TCP experts, let's say. And when this happens, you develop your own language or terminology. So transport layer people, instead of calling packets, they prefer to call segments. But it means the same thing. It's no different. Segment equals packet. And even within transport layer, there's a whole group of people who do TCP, and there's a different group of people who designed another protocol called UDP. Not the same. Even though they're the same transport, they're both transport layer protocols, one group of people call their things segments, the other actually call them datagrams. But they are still packets. And if you go to the network layer people like to call their packets, again, datagrams. If you go down one more layer at the link layer people like to call their packets frames. So in this module, we'll just say packets, and that's about it. So that's why it says you break it up into segments, and then you send one by one. So you get the message from application, you break it up into packets, and then you do your job. Maybe you do some processing, add some headers, then you give it down to the network layer. Okay? And at the receiving side, you do the opposite. You get the packets or the segments or the datagrams from the network layer. You do your job, you strip off some of the headers, but then you combine all the packets together and form the original message. And then you pass it on to the application. And for all practical purposes, we have two transport layer protocols that we operate with, TCP and UDP, but there are many others. Different companies at different times develop their own transport protocol, but they're out of fashion. Nobody uses them anymore. But most of the traffic now is just TCP or UDP. All right. So let's talk a little bit about TCP and UDP and look at some of the services they provide. So one of the basic things that we said, you provide some kind of a logical connection. That's fine. TCP does a few other things. TCP says, I will give you reliability, which means you have given me a message, a whole file. It's my job to make sure everything reaches the destination correctly. That means if any router drops your packet, right? We saw packet drops can happen. So if for whatever reason a router drops your packets, TCP will make sure that we do a retransmission or something else, and then at the end of the day, the receiver will get the whole file, whole message. So that's reliability, right? Another thing is in-order delivery. Last time when we were doing the trace route, we saw that different packets can take different paths in the network. So they all belong to the same message, same file, but every time a packet comes to a router, the router decides, should I send here, should I send there? So different packets can take different paths to get to the destination. So it may be that packet number n takes a longer path, packet n+1 takes a shorter path. So packet n+1 will reach the destination before packet n. So you have to reorder them. TCP will reorder them for you. UDP will not. UDP says, whatever sequence I got, I give to the application. I don't know what's ordering and what those things. Same thing, TCP will recover those losses for you. UDP doesn't care. UDP says, network lost it, it's not my problem. Whatever I get, I give to the application. There's something there called congestion control, right? So when we were talking about these packet losses, why did the router lose packets? Because senders were sending too much data. The router's outgoing links could not cope with it. So then you think, how can I prevent these packet losses? Then you look at the root cause. Why did I have the losses in the first place? I had a loss because the incoming rate, the input rate, the rate at which the senders were sending packets was much higher than what the router could handle. So how will I prevent losses now? Ask senders to slow down. Don't send so much. You're sending at 10 Mbps, I cannot handle. Maybe you should go down to 5 Mbps or 3 Mbps or some number. Right? I should ask the users to slow down. So that's called congestion control. TCP does congestion control. It has a mechanism to figure out that losses are happening, and when losses happen, it signals back to the sources saying, you're sending too fast, please slow down. UDP doesn't care. Right? And of course, now you may think that, oh, UDP is useless, right? Why should I care about this? But then there's simplicity. In order to do this congestion control, reliability in order, you're making the protocol a bit more complex. Sometimes it's okay. You may require that, you may be willing to pay that price of complexity. For some things you may not wish to, right? So you have a choice then. Below congestion control, you have flow control. So what's flow control? So congestion control talks about the problem when sources are sending too fast and routers in the network or links in the network are getting congested. They cannot handle. Flow control is similar but different. So maybe, yeah, I think I can switch this. That's not a problem. And let's say I have these sources. I have a router here. I have a router here. So congestion happens when you send too fast. Everybody is sending a lot of data. And then this router cannot handle. Right? But now let's consider the situation where only one of these is active. These guys are not active. The links are all good. This can handle 100 Mbps. This can handle 100 Mbps. This can also handle 100 Mbps. Right? And let's say there's only one source which is active. And this is sending at 10 Mbps. So then conceptually, there should not be any congestion, right? Everything is fine. You're sending at 10 Mbps, all the links can handle 100 Mbps. But if I look at this destination, this is where you're sending all your data. Maybe this is a computer from the 1990s. Old computer. Its hardware is not fast enough. Its buses inside, they are not fast enough. So this is a slow computer maybe. So you can send as fast as you can, but my receiver is not fast enough, or my receiver doesn't have enough resources. So the receiver gets overwhelmed. And then the receiver can say, oh, please don't send so much. That's flow control. Okay? So flow control is a receiver problem. When the receiver is unable to handle. It's not nothing to do with the network as such. It's not the links and the routers. It's the receiver which is somehow slow. But the whole idea is again the same. You tell the source, please don't send so much. And again, TCP will do this for you. UDP will not do. And the third bullet, there is connection setup. So I want to exchange messages with, let's say, Google. I have two options. One is my computer can contact Google first, say, hey, I want to exchange some data with you. And then Google can say, oh, sure, go ahead. And then you start sending your data. So basically, before you sent your actual data, you had a message exchange with the receiver saying, are you willing to accept my connection, my whatever I'm going to send to you? So you set up some kind of connection. Or you don't care, you just start sending. Right? It's like whether maybe you set up an appointment with somebody, or you just randomly go and knock at their door and see if they're there. TCP will set up a connection. So for example, anytime you try to do a web browsing thing, your browser always connects to the server first, says, I have a request. Are you willing to accept my request? The server will say, sure, go ahead. Hopefully, that's what it'll say. It can also say, no, I don't have time for you. But if it says that, yeah, I'm willing to accept your request, now you can send your data. That's connection-oriented or connection setup. We will look at TCP's connection setup in more detail maybe Friday. Okay. UDP, on the other hand, doesn't care. If you say, oh, UDP, I want to use UDP to connect to this server, UDP will say, just give me the data, and it will directly send the data. So which one is better? Answer is, again, it depends. In some situations, maybe the exchange you want to do with the server is very simple. You want to ask maybe a one-line question, and you expect a one-line or a one-word answer. Very simple. In that case, if you have to set up a connection first, get a response back, and now I ask my question, that's too much overhead. Sometimes you don't want that. In that case, you will use UDP. In some cases, maybe you want to make sure that the server is there, then only you want to transfer data, you use TCP. Right? So these are services provided by the transport layer. Depending upon your needs, you pick which one you like. Okay? So that was TCP. And we also talked about UDP actually at the same time. What UDP does is it basically doesn't provide any of those. So it's a very, very basic protocol. Right? It's what we call no frills and best effort. Means you give me, I will send it. If the server is there, it will hopefully take it. You give me your data, I will break it up into packets, send it. If the network loses something, not my problem, I tried. If the packets are reordered, not my problem, I tried. So that's what this does. So on top, we have the things that the transport layer does provide. There are some things neither TCP nor UDP will provide you or any other transport layer protocol. For example, delay guarantees. If you go to the transport layer and say, can you make sure you will deliver my data within 500 milliseconds? No transport protocol will give that guarantee to you. Same thing about bandwidth or throughput guarantees. If you ask either TCP or UDP, say, can you make sure I will get 100 Mbps? They don't do that. Any questions? Yeah.
So for the connection setup for TCP, it won't send the data until it receives the signal from the server saying
That's correct. So let's say you're the server, right? So I'm going to tell you, can I please have a connection with you? Until and unless you say, yes, it's okay for me to go ahead, I will not be sending the data to you. All right. So now let's look at one service which is provided by both TCP and UDP. And this is one of the fundamental things that a transport layer protocol is supposed to provide. And that's called multiplexing and demultiplexing, right? So what is this multiplexing and demultiplexing thing? Now, if you look at my laptop now, right, I have many applications running. Maybe I have web browsers. And even when I have a web browser, I may have different types of web browsers running. I may have Google Chrome running for something. You know, certain websites don't work very well with Chrome, so maybe I use, let's say, Internet Explorer for it, which is never happens that way. But anyway, let's say I have 2 or 3 different types of web browsers running. Maybe I have Skype running. Maybe I have Outlook running for email, right? Maybe I have a radio player of some kind running. So there are many different applications that are running on my computer at the same time. Now, my physical layer, my Wi-Fi or my wireless thing, picked up a packet, gave it to the link layer, gave it to the network layer, gave it to the transport layer. It's for my computer, that's fine. But this particular packet, the data in that packet, is it for a web browser? Is it for Skype? Is it for my Outlook? How will I decide? Let's say they're all using TCP. Right? Outlook uses TCP, web browsing uses TCP, and so on. So TCP has got this packet, and now it needs to know which application. That's multiplexing and demultiplexing. So somehow the transport layer has to look at the packet and say, oh, you need to go to web browser. And even within the web browser, I have 15 tabs open right now. Which particular tab should it go to? That's again multiplexing and demultiplexing. Okay. When we think of multiplexing and demultiplexing, the way you want to think is that, we talked about applications, right? We have applications running on computers, but from a more of a operating system jargon, these are processes running. Right? My web browser is a process. My Outlook thing is a process. Skype is a process that's running on my computer. And let's say my Skype process or my web browser process wants to talk to the web server process, which is running at Google. So what we are really trying to establish here is inter-process communication. If you have done an operating system module, you would have done inter-process communication. It's just that in that case, most likely, the processes were both running on the same computer. The difference in a network is that the processes are not running on the same computer. You have process on computer A, which wants to talk to process on computer B. You're trying to facilitate this communication. Now, in order for my web browser process to send data, it has to take whatever its data is, it has to give it to TCP. What is TCP in terms of operating system? It's again another process which is running in my computer. So my application layer, that particular process, has to give its data to TCP, which is another process. How do we do this? Usually through an API, right? Programming interface, application programming interface. For the network world, these APIs have a name, and that's socket. Okay? So we have to create sockets. So your application or whatever has to create these sockets, or the operating system can create these sockets that will allow your application process to transfer the data to the TCP process. And the process which is running on, let's say, my laptop will then talk to the process which is running on Google. And the way we do the multiplexing and demultiplexing is by looking at which particular socket you want to connect to. So let's take an example here. So at the sender side, the multiplexing or demultiplexing, you will take data from different applications that are running at your end. Maybe you will add some identifier which will identify which socket you're trying to talk to on the other side and which socket on your side is sending the data, and then it will send it out. And at the receiver side, you will do the opposite. You would again use the socket information saying which socket somebody is trying to send data to, and then you will use it to decide which particular application your data goes through. Now, the way we identify this socket, the identifiers we use to say, oh, this is the socket I want to go to, depends whether it's TCP or it's UDP. Okay? So in general, if I talk about sockets, we have to identify. How do I identify? Usually there are two sets of numbers associated with every computer and every process. One is the IP address. So we haven't talked about the network layer yet, but every computer or every interface on your computer, interface means Ethernet or Wi-Fi or any link that you're connecting to, will have an address called an IP address. We'll talk about that more. But at this time, just take it that IP address identifies your computer. But within your computer, you have many different processes or applications running. And different applications or different processes will again then be identified by using something called a port number. Okay? So if you have HTTP server running, it will have a port number which is called 80, which is usually given some number 80. Okay? Something like Telnet, I think Telnet is port number 23, and so on. All right. So when you create a socket, you would have an identifier associated with that socket, and that identifier will be a combination of these IP addresses and port numbers. UDP will have a different combination. TCP will again have a different combination of these IP addresses. Okay? And this is what a UDP packet actually looks like. The way you want to interpret this is, hang on just a sec. This is what a packet looks like. These are 32 bits. These are the next 32 bits. These are the next 32 bits. These are the next 32 bits, and so on. Okay? Each row consists of 32 bits. And here you see some information, which is port number at the source, port number at the destination, and these will be used along with the IP addresses, which I'm not showing here, to identify which socket you are going to, and then that will be used to multiplex or demultiplex you. Okay, let's take an example to make this a bit more clearer. And let's start with UDP. UDP is connectionless. That means you want to send data, just send it off. So let's say I'm a server, I'm running some application, and you are all the clients, and you can connect to me. When he sends the data to me, it goes to the socket that I'm running. If she sends the data, it will also go to the same socket. Okay? It will go to the same process. So how will we identify this? So in this case, let's say the application running there, the port number we have assigned is 9157. Okay? And when we do socket programming, you will see how we can assign these port numbers and so on. So as a programmer, you will have some flexibility in choosing the port numbers and assigning them. So let's say you have created a socket, and the port number associated with that socket is 9157. Somebody else on another computer has also created a socket, and the port number associated that they assigned to it is 5775. And at the server here, we have an application running, and the socket associated with it has the port number 642, it's 8, I guess. On top of this, this has an IP address, this has an IP address, this also has an IP address. So when this particular computer sends a packet to the server, the packet will have some headers, right? Just like we showed earlier. And then the header has this source port number and the destination port number. So in this particular example, since the, the machine on your left is sending, it says my source port number is 9157 and the destination port number that I want to go to is 6428. When this packet reaches here at this particular computer, it will go through the physical layer, go to the link layer, go to the network layer, go to the transport layer. Now the transport layer's job is to do the multiplexing and demultiplexing. In general, there would be other sockets also running here. I'm only showing one socket. There are many other sockets running. Which socket should I pass through? In the case of UDP, it will just say, okay, what is the destination port number? What is the port number associated? I'm the destination. What are the different port numbers for the different sockets? Whichever is 6428 gets this packet. Okay. Similarly, if the other machine wants to talk, okay, okay, I jumped, I guess. And if this particular server wants to reply back, when it replies back, the source port number is 6428, right? Because this is the machine sending the message. And it wants to talk to the process here. So it will tell, at the destination, please go to port number 9157. So in the reverse direction, the source and destination ports will get flipped. But now let's come back to the more interesting part, that what happens when process number 4 wants to talk. So when process number P4 on that machine is trying to send, the source port here will be 5775. Right? And it's trying to talk to process P1 running on the server. And that process number is 6428. So that the destination it wants to go to. Six, 4, 2, 8. Now, as before, when this packet comes through, it will go through the physical, it will go through the link, it will go through the network, it will come to the transport. And there are many other sockets here, each with their own specific port numbers. And then TCP will see which is the port number with 6428. This is the port with 6428, and it will go through this. And even though I have erased it, if you remember, when this guy sent the packet, we also transferred the packet to the same port, same socket. This guy sends, goes through the same socket. So it's the application's job to keep track who is sending what, and distinguish between them, whatever it needs to do. But as far as UDP is concerned, because this is connectionless, it will just say, how do I identify which process you're going to? I just look at the destination's port number and send it through there. Okay. Let's look at TCP, and hopefully that will clarify a few more things, and then we'll come to questions. So how about TCP? In the case of TCP, it is connection-oriented. Connectionless means I've closed my eyes. I don't really care who is sending what. I will just look at the destination IP address and port number, and I can send. But when I establish a connection, I say, okay, I have a connection between these two. I have a separate connection between these two. So you are connected to Google, let's say, using TCP. Google keeps a separate special connection just for you. Somebody else connects to Google, they will have a separate connection, separate socket just for them. Right? So when it comes to connection-oriented, every connection essentially gets a separate socket. In the case of connectionless, there's only a single socket, and all people are connecting through the same single socket. Connection-oriented, we will have different sockets for different connections. So let's see. In the case of TCP, each socket will be identified by 4 things. What is the IP address of the source? What is the port number of the source? What is the IP address of the destination? What is the port number of the destination? If any of these changes, you have a different socket. Right? So let's see. Here's an example. Just like before, I have 2 computers and let's say 1 server. Each one of them has its own IP address. This is A, this is B, and this is C. Right? And let's say I have a socket here. This would have some some port number. And in this case, the port number is 9157. Right? And here, I have two ports, and two sockets, and in the middle I have 3 sockets. So when this particular process, let's say, wants to connect here, the source IP is A, the source port is 9157. And let's say the one in the middle is a web server, Google, let's say, right? And web servers always run at port number 80. Right? So the destination port number, that's why at the bottom you see is 80. And when I send the message, I'm sending, I will say the destination IP address is B. Please go to B. And when you go to B, I want to connect to port number 80, web server. So I send that back. Now imagine there's another computer here, computer C. Computer A, for itself, chose port number 9157. I chose port 9157. Can I dictate to you guys, you will not choose port number 9157? No. You're running your own computer, you can choose whatever port number you want to. Of course, there's a range, but you can choose. So in this particular case, let's say C has also chosen 9157 for itself. Perfectly valid. C has its own IP address, which is different from it cannot choose my IP address unless it wants to spoof and other things, but in general it cannot. It will have its own IP address. It wants to connect to Google. So destination is B. B is Google. And it wants to connect to Google's web server. So the port number for the web server is 80. So it also says 80. This message also comes to Google. My message also comes to Google. Physical layer, link layer, network layer, transport layer. At the transport layer, now TCP has to decide where should it go. Which process should it go to? Previously, in the case of UDP, connectionless, it would have just looked at 80 and 80 because that's the destination port number, and they would have both gone to the same socket. Now it's different. TCP uses more than just the destination port number to decide the socket. It looks at all these 4 things together. Okay? So when I look at all these 4 things together, they are not the same. One element is different. Here I have A, here I have C. So they are 2 different. As far as the identifier goes, they are 2 different things. So here they will go to 2 different sockets. Okay? And this was a much more benign example where, the same computer C, it also wants, that's like 2 tabs on, the browser on C has 2 tabs open, both are going to Google. So the destination is still B, and it wants to connect to the port 80, which is the web server at Google. And then, I have chosen a different port number for myself at C. So this is easier to visualize, but this was the example at the bottom was a bit more complex example. So where 3 of the things were the same, you're both trying to connect to the same web server. Somehow you're both using the same port number, but because your IP addresses are different, all the 4 elements are not the same, so the identifier of the socket is different. So it's going to end up at 2 different sockets at the destination. So in another way, if you look at the Google server, it's maintaining a separate socket for every connection that it has. That's easy to visually imagine when you think about, it's connecting to 2 different computers or 2 different sockets. But even when it connects to the same computer for, let's say, 2 different tabs, I will still use 2 different sockets. Questions? Yeah. So now the question is about threads, right? So if you look from an operating system point of view, you have processes which are a bit more heavyweight, and to save on resources and so on, you can use threads which are much more lightweight. So the question was, will I create a new socket for every thread? The answer is it depends on your operating system and the way it handles things. In the old days, they would actually create different sockets. Yeah. Yeah. Because this is connection oriented. So everybody who wants to connect to me, I will treat them on a unique thing. I will give a separate socket to everybody. That's connection oriented. That's TCP. And so that's web browser. Web servers use TCP. So every time anybody connects, the server will give them a separate socket. The previous one, where they all went through the same socket, was UDP and connectionless. So there I don't care about you, I don't treat her and you separately. You are both connecting to me, same socket. I'm not maintaining individual connections with everybody. So that's why they go through the same socket. Yeah. Yes?
What's the distinction between a socket and a port?
So a socket is the API. It's the interface, application programming interface that the operating system will provide applications to talk to the transport layer. So that's the API. Now I can create many APIs. They should have some identifier, something to distinguish them. So the port thing is just a number I assign. So port doesn't really mean much. It's just one of the numbers or one of the fields I use to identify a particular API, which is a socket. Okay? So let's say in your laptop you have many applications running. They all want to use TCP. So you will ask your operating system, please create a socket for me. Once they create a socket, they will assign a number to it to identify it, and that number will be a port number. But in reality, it's not just the port number, also the IP address, everything together will identify it. But port number is one of the things that will be used to identify that socket. Does that clarify you? Yeah, okay. Any other questions? Yes. Okay, so let's let's go here maybe, right? Right, so this is some, let's say this is A, this was C, this was B for us, and let's give some number. Let's say this is 5,000. The port number here is 5,000. And let's say the port number here is 6,000. And the port number here, you want it to be the same, right? So this is also 6,000, right? So what will happen is when I send a packet here, so it will have source, destination. So this will say 6,000, and this will say 5,000. And source here is 6,000. This is 5,000. When it crosses all the layers and it comes to transport layer, it will just say, okay, which port you are going to? 5,000. It will go through this socket. This packet, when it comes to transport layer, will say, oh, this is connectionless. You want to go to port number 5,000. This is the socket associated with port. So they will both pass through the same socket. They will go to the same application layer process which is running. Now, sorry. All right. Okay. Now, it is possible that the application here will want to reply back to them. How? When it replies back, SRC and destination, the source here will flip, will become 5,000, destination will be 6,000. But it's not just the port, you also add what is the IP address. This is coming from B, this is going to A. When it sends it back, it has to specify the IP address. But when it receives the message and it wants to check which socket it wants to go to, it doesn't look at the IP address. TCP will look at the IP address. UDP will not. But when you have to reply back, you have to specify the IP address. Yeah. Yeah. Yep, they can use the same port number. So for example, if I go back here, in this case, B had 3 sockets. They all had the same port number 80. Okay? But just the port number doesn't identify the socket. 4 things here were identifying the socket. So you can still distinguish between sockets. Anything else? Yeah. Collision in the same port. So in this case, the example that by collision, I assume you mean that now, in this case, I have one example of, I guess, one type of collision where 2 different computers were connecting to me and they were both using the same source port number. It can happen, but that's not a problem because when I reply back to them, they have different IP addresses. This is coming from A, this is coming from C. The same socket will send out the reply back, but when it sends the reply back, it will say, oh, go to port number 6,000 on A. Go to port number 6,000, but on C. So that's not a problem. Can I have another socket here with the same 5,000? That's another collision with connectionless. The answer is no. You will not be able to distinguish between them. Because in the case of connectionless transport protocols, you only look at, I have received something, which port number you want to go, which socket you want to go, how do I look at it? Port number. If I give the same port number to two different sockets on me, then I will not be able to distinguish. Is that what your question was? Okay. All right. So now let's go back to UDP, I guess. So we talked about multiplexing and demultiplexing. So now let's take a look at the most basic transport layer protocol, which is UDP, and that's connectionless. So UDP is also called what is called no frills, nothing fancy here. It's a very bare bones, basic minimum kind of thing, and it's best effort. So you give something. So what will UDP provide? UDP provides just two things. It provides this multiplexing and demultiplexing for you. And then the second thing it provides is, once it gets a packet, it can check for you whether there are any errors in it or not. That means, the sender may have sent a 1, somehow you got a 0. It can do that error checking for you. It can tell whether there's an error or not. It cannot correct that error. It will just say there's a mistake here. I don't know what that mistake is, but I know there's a mistake. So there's two basic things that it does. Okay? So since it doesn't do like reliability in order, so you may lose packets. Packet number 50 may arrive after packet number 60. That's possible. Right? And it's connectionless. So there is no handshaking. Handshaking means before I send data to you, I don't exchange any messages to set up a connection with you. I just directly blast my data to you, right? So it's connectionless, no handshaking, and every UDP segment or packet or datagram that you get is treated independently of the others, right? So these are straightforward. So now you may say, why would I use this? And some of the things are like, it's fairly simple. I guess I will come to that later on. But even it doesn't provide so many things. It's so basic. There are still some services where it makes sense to use UDP. The most common one is actually something called DNS. And when you learn about application layer protocols, you will look at DNS. But just to give you a very quick introduction to what DNS does. In the examples that I was doing earlier, we said, I want to connect to Google's web server. So I say IP address of Google and port number 80. But you think back, have you ever entered the IP address of Google ever? You don't even know what the IP address of Google is, right? So in your browser, what do? You type www.google.com. Or www, you want to read news, you say www.bbc.co.uk or wherever you read your news from, right? Or you say www.nus.edu.sg. Computers don't really identify themselves by names, right? They're not humans like you and I. They need IP addresses. IP addresses used to be 32-bit binary numbers. Now they're 128 bits. So you and I cannot remember. I cannot remember 32-bit binary numbers. If you really push me hard, maybe I'll remember 1 or maybe 2. But beyond that, I won't, right? So humans find it easier to remember names such as www.google.com. I cannot remember 32-bit binary numbers. But the computer world works on these 32-bit binary IP addresses. So what DNS does, it does the translation. You tell google.com, DNS servers will translate, oh, google.com is 128.113.56.25, something. So every time you type www.something.com in your browser and you hit enter, the first thing, before it even contacts Google, is DNS. Your computer asks some servers, maybe operated by NUS or Singtel or whatever, to say, can you please translate google.com to the equivalent to its IP address? So you send a query to a server, say google.com. The server is supposed to reply with the IP address. It's one of it's one of those one-line transactions, right? You ask google.com gave. So it should be fairly simple and it should be quick. But if I have to set up a connection with the server says, yeah, fine, go ahead, ask me your question. Then I ask my question, then it does my translation. It's more steps, and of course it takes longer. Right? So in this case, just use something simple as UDP. What's the worst that can happen? Maybe the network will lose your query. Right? Fine, you lost my query. I just see my browser is not doing anything. I get impatient, I will hit enter again. Then it'll resend the query. It's not too bad, right? So in those cases, So in situations like this, UDP may make more sense. And there are similar other things like SNMP, that's a simple network management protocol, and also for applications such as streaming audio or video. If you're streaming audio and video and one packet gets lost, are you going to pause your video? You're watching World Cup final, let's say, right? And one packet got lost. Would you prefer to see a little bit of glitch in the screen, but the video continues? Or would you prefer that your video pauses, TCP kicks in, recovers the loss, and then you can watch your video again? Personally, if you ask me, I'm okay with a little bit of glitch or a little loss of audio, but the whole thing continues. It doesn't pause my video in the middle. So for those applications, again, UDP may be useful. And if you really, really want this reliability and other things, but you still want to use UDP, your only option is application layer. You're the one. This TCP, UDP, network layer, they're all part of the operating system. So usually you and I, we don't touch it. The only flexibility we have is, I can write my own application protocol. So if you want reliability, but you still somehow want to use UDP, it's your job as the application developer to somehow take care of reliability at the application layer itself. All right, so now let's look at what a UDP packet looks like. It's actually quite simple. Again, this is how we will look at packets in this particular module. Packets will be represented like this. And each row is 32 bits. And since there's a line in the middle, that means the first 16 bits of the packet are used to denote the source port number. The next 16 bits denote the destination port number. So these are the ones that I will use for multiplexing and demultiplexing. Okay? So the first 32 bits, first 16 bits is the source port number. The next 16 bits is the destination port number. Then I use another 16 bits to denote the length of the packet. Not all UDP packets would be of the same length, right? So I may send more data, I may send less data, but I have to tell how much data I'm sending, what is the length of this packet. So I use the next 16 bits to denote what is the length of the packet. And this length is counted in units of bytes, and it also includes the length of the header. So in this case, headers are 32 bits and another 32 bits. So these are the headers. And this is the actual data. So the headers are 64 bits, 32 plus 32, so that's 8 bytes. So no matter what data you send, UDP will always tack on 8 bytes of extra headers. So that's the overhead or the price you pay. Okay? And then the last 16 bits in the second row are something called checksum. And that is used for doing error checking, to check if there are any errors in the packet or not. Okay? And we talked about all these things, and the advantages of UDP, but let's talk about the checksum a little bit. The whole objective of having a checksum is to detect during transmission whether there was a problem somewhere and some of your bits got flipped or not. Okay, it helps you to check that. And the whole idea is sort of like this, right? So let's say this is your data. And your data, I can break it up into rows. These will all be binary things, right? 32-bit binary, whatever you are. But we are humans. Let's just give them numbers. Let's say this is 5, this is 27, this is 36, something like that. Just to visualize things, right? So I am sending 5, then 27, then 36. What I can do is, I can send this 5, I can send this 27, I can send this 36, and one extra thing. What is that extra thing? Let me add all of these up. 5 plus 27 plus 36. All right. I should have chosen smaller numbers. So 50, 63, 68 is my guess. Okay? I put 68. So I send the original data plus one extra thing, which is the sum of all of these. 68. So now at the receiver, you get these. You have received these. You take this, you take this, you take this. You add them again. Is this the same as the received sum? If they're same, you have some confidence that, okay, nothing bad happened. Everything is probably okay. But let's say during transmission, any one of these 4 things changed. Maybe somehow this became a 37 during transmission. Then this will come out to be 69, and these will not be equal. That's sort of the intuition behind checksum. You send the data, but you also add up all the data, and you send the sum. At the receiving side, if the received data and the sum, they don't match, then you have some, gives you a hint that maybe something went wrong. And the way checksumming will be done in the real world is, you will take your data 16 bits at a time. Right? And this includes the header also. So you take the first 16 bits, then the next 16 bits. Add them. Simple binary addition, right? So let's say the first 16 bits were this 111001100 something, and then the next 16 bits. You add them. So 0 plus 1 is 1. 1 plus 0 is this. 1 plus 1 is 2. 2 in binary is 1, 0, right? So I put a 0 here, and I have a carry of 1. So 1 plus 0 is again 1. This is 1 and 0 is 1, 1 and 0 is 1, 1 and 1 is 2 again, so I put a 0. I have a carry of 1. Simple addition. Once I do this, I observe that I have an overflow here, right? If you have an overflow, what you're supposed to do is, you are supposed to wrap it around. Oops. Then you bring it back here and add it again. So these were the first two numbers. If you have more data, take the next 16 bits, add to it. The next 16 bits, add to it. Next 16 bits, add to it. Keep doing this. What if my data is not a multiple of 16 bits? What if my data is somehow, let's say, only 3 bytes? Add extra zeros in the end. Use padding. Okay? But you take 16 bits at a time and you add them up. Keep adding. If you have an overflow, bring them back. Finally, this is the end sum after you have added everything together. And this is the sum you get after adding all your 16-bit numbers. You do a ones complement on that. Means flip the zeros to ones and vice versa. So here you did a ones complement. And you got this ones complement thing becomes your checksum. So if I go back to my packet structure here, let me erase everything here. Right. So I will take this first 16 bits, add it with this next 16 bits. Whatever the result, I will add it with the length. Whatever the result, I will add it with the first 16 bits of the data. Then add it with the next 16 bits of data. Then the next 16 bits. Then the next 16 bits. And so on. I will add everything together. And in the end, whatever result I get as the sum, I will do a ones complement. And that result, I will put in the checksum field. Good? And then when I transmit, I will transmit all of these together. Yes? Yes. Let me come to that. Why wouldn't I just directly send the sum? Right? It is motivated by efficiency. And you have to think 1970s now. Of course, you could calculate the sum, and you have the checksum, and you do a comparison. Are these two numbers equal? Right? But let's say what is done at the receiver. At the receiver, you take the whole, everything that you have received, and do the sum. If there are no errors, it should be all ones. Right? Because, let's go back to this. Let's say the sum here was 101. It's not 16 bits, but imagine it's 16 bits. Now you do the ones complement on this. So this will be 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0. This is what you sent as the checksum. At the receiver, so no errors during transmission. If I do the sum, I should still get this. And now if I add the checksum to it, I will get all ones. And back in the day, comparing whether a register has all ones was much more efficient. So at the receiver, what you do is add everything and check if it is all one. And you're done. You don't need to compare two numbers where you got to do a bit by bit comparison. It's just slower. Yep. Yeah. Yeah. So you could have said, oh, you're not doing anything anyway, so why are you even bothering? Yeah. So this is historical reasons. It's just some basic thing which they're providing you to see whether something is wrong or not. But yeah, you could say, you're not doing much, don't do this also, whatever you get. Yeah. Now, even though this is a it's trying to check errors for you, it's fairly easy that it's fairly easy to see that the protection or the detection capability that it provides you is not really that great. Right? For example, let's say you transmitted. Somehow this became a 0, this became a 1, and let's say this became a 1, and this became a 0. Your checksum won't change. You will still detect everything is okay. But in reality, your data is not the same. Right? So what it provides you, in other words, is it does not guarantee that it will detect every possible error. But if it's just one bit or some combination, certain combinations, it will be able to detect. It's not a foolproof error detection mechanism, but if your errors are not too many, just one bit here and there, it should be able to detect. That's the idea. Questions? Yeah?
So is the wraparound added every single time?
Every single time.
And then it's only once you add it?
At the very end. It doesn't matter, but you would usually do it at the very end. All right. So, moving on then. So one of the biggest things that UDP provides, UDP doesn't provide anything much, but one of the biggest differences between TCP and UDP is that TCP provides reliability. Right? So what is that reliability? Which says that if the network somehow loses any of your packets, TCP will make sure that it will recover that loss. So before we get into exactly how TCP does its loss recovery, let's look at the loss recovery problem from the fundamentals, right? So what are the basic, how could you design a reliable protocol, right? How would you go around designing a reliable protocol? So let's start from something very simple, and then we will slowly build it up. Right? So this is the main problem, that you transmitted something. Again, you see this picture says frame, but it's a packet. Anyway, you transmitted something, and then the receiver didn't get it. Now, your communication may be unreliable from 2 points of view. One is what this packet is showing. I sent something, the receiver didn't get it. So most likely it was dropped somewhere along the way. Maybe some router got overflown, and then it dropped my packet. That's one possibility. The second possibility is that maybe the receiver received what I sent, but there was an error. Maybe my checksum said, oh, there's an error. So even though the receiver received the packet, it's of no use. The data is incorrect. So again, you have to throw it away and say, ah. So in both cases, I would like to be able to recover this. Right? So how would you do this? Now, if you think about human conversation, if I'm talking to you face-to-face, it's a bit different. But imagine you're on the phone, and you're not really sure whether the other side is hearing you or not. So what do? You expect the other side to occasionally say, yeah, or okay, some kind of feedback to you, which gives you confidence that the other side is able to hear you. We do the same thing in the network world also. If you want to be sure that the other side has received your packet, then what you can do is you can say, okay, I will come up with a protocol where I will send a packet, but then I expect the other side to give me explicit confirmation that they have received the packet. Unless and until I get that confirmation, I will stop, I will wait, and I will not move along. So if I get that confirmation, and in the networking world we'll call it an acknowledgement, Once I get the acknowledgement, sometimes we will shorten it and say ACK. Once I get the acknowledgement saying I have received, then I'll move on to the next packet. Fair enough? But then, in this particular example, the receiver never received the packet. So what acknowledgement will it provide? So I'm just waiting. How long should I wait? So most protocols, what they will say is, they will say, have a timer running at your end. Put some reasonable value to it. If the timer expires and you still haven't received an acknowledgement, please retransmit. That's a very simple protocol, and that's what we are doing here. And there's a name for this protocol. It's called stop and wait. That means every time you transmit a packet and you go one by one, you cannot transmit 50 packets. You transmit only one packet at a time. You transmit that packet and you have to stop and you have to wait for the acknowledgement to come back. If the acknowledgement comes back, very good, move on to your next packet. If you're waiting, you have waited long enough so that your timer has expired. So you have a timer running with a timeout value. If you receive your acknowledgement before that, everything is good and you can move on to the next packet. But let's say for some reason you did not get the acknowledgement, and in the previous picture here, it's the data which was lost, but the internet doesn't discriminate, right? It can lose your packets. It can also lose the acknowledgements that are coming. So that's sort of what is showing here. If maybe you sent a frame or a packet, it was received, but the acknowledgement didn't make in, or maybe the packet got lost, you didn't get any acknowledgement. Either way, you are waiting for the acknowledgement, you didn't get it, and then there's a timeout, so you retransmit the packet. Okay, so very basic. So stop and wait. Now, while intuitively it seems to make sense that this should work, but it turns out that some special cases may happen, in which case you will get into trouble. Right? So let's look at those special cases, and then hopefully they will motivate us to enhance this protocol in a way. Imagine this situation. I said we have to choose the timeout value appropriately or smartly or something. But it's still a guess. Right? I'm trying to contact, let's say, www.cornell.edu. What's the right amount of time to wait for a packet to go to upstate New York and then come back? I don't know. 2 seconds? 5? Should it be 500? So some number, right? But again, still it's a guess. And even though we will not go so much into detail in TCP in this particular module, TCP has a way of estimating these times. Right? Anyway, so let's say I made a guess. Right? I made a guess, but the guess was wrong. This was my timer value. The acknowledgement didn't come in time. So I thought my packet was lost. So since I thought my packet was lost, I retransmitted the packet just before the acknowledgement came in. But if you look at the receiver, it got 2 copies of the same packet. So it thinks this is packet 1, this is packet 2. Is it possible in real life that 2 packets that you send would have the same data? It's possible, right? Imagine you're sending temperature readings. The temperature of this room hasn't changed, so the data wouldn't change between 2 packets. And this is an example I made up, but here the problem is now that the receiver doesn't know. Are they 2 different packets or are they duplicate packets? So in order to solve this, what we need to do is we need to add numbers or identifiers to packets to identify each packet individually. So what we got to do is we have to say, oh, this was packet 0, packet 1, packet 2, packet 3, and so on. Now there are 2 things I want to highlight here. One is, when you're designing a protocol as an engineer, one of the things for you as an objective is to make it as simple as possible and to keep the overhead as low as possible, which also translates to make your protocol as efficient as possible. So here we saw that we need to add sequence numbers to packets. Where are we going to add these sequence numbers? They're going to be part of your headers. So in UDP, you saw source port number, destination port number, checksum, and length. Now, if you were to make it reliable, you have to add another field there, which will be sequence number. And that's going to be overhead, right? So my port number, destination, checksum, and length, they were all 16 bits. How many bits should I use for my sequence number? 2 bits, 4, 16, 32, 64, whatever, right? I can use any number, but I want that number to be as small as possible. I should pick the least number of bits that will get my job done. And in this case, in the stop and wait case, it turns out that 1 bit is good enough. Why? 1 bit will allow you to distinguish between 2 things, right? 0, 1. When you are doing stop and wait, you only send 1 packet at a time, not 2, not 3, right? So the only confusion that you may have is this a new packet or an old packet? So you have to distinguish these 2 things. So 1 bit turns out to be good enough for that, to distinguish old or new. So the first time you send a packet, you call it number 0. The next packet you send, if you're repeating the same, if you're retransmitting it, it's still packet 0, right? Let's say you got the acknowledgement, and now you're transmitting a new packet, it's packet number 1. You got the acknowledgement, you want to transmit a new packet after this, you should call it packet number 2, right? But in this case, I don't need to keep track of packets that were transmitted 3, 4 times earlier. I just know that the last packet I transmitted was good, so this is a new packet, so I just alternate. If the previous one was 0, this is 1. If the previous one is 1, the new one will be 0. Right? So it suffices. Yeah, so that's one. And then the other thing is that, the acknowledgements. It turns out that we also need numbering for the acknowledgements. You could say, Prof, do I really need to add numbers to ACKs also? Turns out that yes, you do, and here's an example to show that to you. So for example, let's say I sent packet 0 first. Was received correctly, so the acknowledgement was sent. And now, let's say I don't add numbers to the acknowledgements. But let's say I made a mistake in my timer value. I had a premature thing. So I think that you have not received, so I retransmit the packet again, packet number 0. Okay? So in the meantime, the acknowledgement for the old packet has come in here. What does the sender think? As far as the sender is concerned, this was lost, right? The timeout occurred and I didn't get anything, so this must have been lost. Now I resend the packet, and I got the acknowledgement. I have no way of knowing that this is an acknowledgement for the older packet. So since I think that the acknowledgement has been received, I send the new packet, which is now 1. But this got lost. But the older packet, retransmitted packet that I had sent, this was received correctly, so the acknowledgement will come back. And what I will think is, this is acknowledging packet number 1. And I'll move on to the next packet. And that's not right. And this problem happened because the acknowledgements did not explicitly say which packet it was acknowledging. So if I take out the numbering from the acknowledgements, I can potentially get into trouble. So it is important to add the sequence numbers to the acknowledgements also. Questions? No? All right, then I think this is a reasonably good time for us to stop. It's at 34. When we come back Friday, then we will continue from here.